This is the video for section 4.3, homogeneous linear equations with constant coefficients, which from here on out I am going to denote as HLEX. So as you know, homogeneous linear equation, we all know what that means. Constant coefficients, of course, means that all of my coefficient functions are just constants. So we are going to develop a general method of solution for higher order HLEX, and it's going to be motivated by the following. Let's consider a first order HLEX, ay prime plus by equals 0. So this, of course, we can solve using separation of variables. And if we set y prime equal to minus b over a, divide by y, integrate, yada yada, we see that our solution is y equals our initial condition, y naught if we have one, times e to the minus b over a times x. So we see that this first order HLEX has its solution as an exponential. So e to some constant times x. And that's going to be our motivation for the method we're going to use to solve higher order HLEX. So our general method of solution is we're going to suppose that our solution is of the form y equals e to the mx, again motivated by the first order case, and then we're going to use our ordinary differential equation to find and solve for m. So let's see some examples. The second order HLEX is ay double prime plus by prime plus cy equals 0. How are we going to start? We're going to assume we have a solution of the form y equals e to the mx, which would mean y prime equaled m times e to the mx, and y double prime is m squared e to the mx. If we put that into our second order HLEX, we see that we have the equation am squared e to the mx plus bm e to the mx plus c times e to the mx equals 0. And of course we can factor out an e to the mx. So we have that times am squared plus bm plus c equals 0. E to the mx is non-zero. So we're left with this quadratic equation in m. Am squared plus bm plus c equals 0. And that is called the auxiliary equation. And of course, since it's a quadratic, we can always solve it, and we know exactly how to solve it. It is, we have the quadratic formula. So we have two roots. They may or may not be distinct, and they're given by minus b plus or minus the square root of b squared minus 4ac over 2a. So solving the second order HLEX just reduces to finding the roots of this second order auxiliary equation, which is just a quadratic. So we have three possibilities that could happen in the second order case. We could have both of those roots be real and distinct. And in that case, our two solutions would be y1 equals e to the m1x and y2 equals e to the m2x. So you should check that those form a fundamental set of solutions. So remember, that means you want to check they're both solutions, check that they are linearly independent, and there's two of them, which is the right number for a second order differential equation. So if you confirm that they are indeed a fundamental set of solutions, then the general solution is given by y equals c1 e to the m1x plus c2 e to the m2x. The second case is if both of our roots are real, but they're equal to each other. So in this case, we get one solution, e to the m1x, but unfortunately, we couldn't just say y2 equals e to the m2x, because that would be the same as y1, and two copies of the same function, unfortunately, do not form a linearly independent set. So what you will see, or what you have seen in homework 4.2, is that you can use reduction of order to show that indeed the second solution is x times e to the m1x. And once you check that these form a fundamental set, so namely they're solutions and they're linearly independent, then you get that the general solution in this case is y equals c1 e to the m1x plus c2x times e to the m1x. Case 3, that both roots are complex, so they're complex conjugates. They're a plus or minus b times I. And here, since we're dealing with real numbers, our coefficients are all real, we want to have our solutions written in terms of real numbers. And we'll go through the derivation of what I'm about to say in class, but basically it reduces to an application of Euler's formula that e to the I theta is cosine theta plus I sine theta. Again, we'll talk about it in class. But in this case, your two solutions are e to the ax times cosine of bx and e to the ax times sine of bx. So again, check these are a fundamental set of solutions, and then your general solution is just a linear combination of these two. In the higher order HLEC case, we would have something that looks like this, an nth order HLEC. We're going to do exactly the same thing. We're going to assume we have a solution of the form e to the mx, and then we're going to take all of our derivatives up to order n, and we're going to plug into our differential equation. We're going to factor out the e to the mx, and what you will see, and what you should convince yourself, is that the auxiliary equation you're left with is a sub n times m to the n plus a sub n minus 1 times m to the n minus 1, etc., plus a1m plus a naught equals 0. So finding solutions of my higher order HLEC is just equivalent to finding roots of this nth degree polynomial. Now for n greater than 2, we don't have such nice classifications of each possible case, so you just sort of have to find your roots and go from there. Right, find the roots of the nth order polynomial. So let's see a short example. Let's find the general solution to y double prime minus 5y prime plus 6y equals 0. We are going to assume that we have a solution of the form e to the mx, which means that our auxiliary equation is m squared minus 5m plus 6 equals 0. You should check that. Factor it, I get m minus 2 times m minus 3 equals 0, which means that my roots are m equals 2 and m equals 3. So that means, since they are two real roots and they are distinct, by what we said earlier, y equals c1 e to the 2x plus c2 e to the 3x is the general solution of the second order HLEC.